Mohan, a lot of thanks for taking this interview. Let's
Thank
start
you.
from the most famous story about you, the ARIES algorithm, which has a huge influence in database fields. So could you please share with us the behind the story, why it has a huge influence on database field and how it was proposed?
Chen-Ying, it's a pleasure for me to be interviewed by you. I've been a database person from the time I was even an undergraduate student back in India when I was a chemical engineering student. And there was no possibility at the time in India of doing a bachelor's degree in computer science. So I got excited by computers technology, but I could only just use the system. But in a formal sense, I had to wait till I came to the US to do my PhD in computer science at University of Texas at Austin. And subsequently, I joined IBM Research. And so when I first came into IBM Research in San Jose, this is the research lab which gave rise to the concept of relational databases and also the first serious implementation in the context of which the SQL language got developed. So the project was called System R. I joined the follow-on project to that System R, which was called R-Star, a distributed database project, which was December 1981. I was given a very specific area to focus on because a guy who had been focused on transaction management, so-called distributed transaction coordination, he had left a while before. A very famous guy, Jim Gray, who much later wound up getting the Turing Award, the highest award, most prestigious award in computer science. That first piece of work I did also became a well-known algorithm. It was called presumed abort, and it became an international standard and all that. But really at the end of that project, IBM Research decided and built a brand new database system, which will be from day one more extensible and address more modern requirements than what the pre-existing systems had addressed. That I said, even though the initial focus of the project were extensibility and client server, I said, I have come to know about some open problems that the original System R people had not been able to solve. This is the so-called fine granularity locking or record locking with a particular way of doing recovery called write-ahead logging. So that had remained as an open problem, and hence IBM products had gone out with something bigger than a record level kind of locking, page locking, which in the field was getting the product into a lot of trouble because customers were facing concurrency conflicts and elongated response times and such. They were not able to run many transactions in parallel without them interfering with each other in bad ways, because the first transaction that modified its record would have grabbed a lock on the whole page, and that would prevent from the second transaction simultaneously trying to modify another record on the same page compared to the one that the first guy had modified. The granularity of locking was bigger than a record, namely a whole page. That sort of problem had been pain, not just at IBM. So it's that problem that I said I'm going to now focus on. The ARIES family of locking and recovery algorithms got invented. I came in with a fresh mindset without the baggage of having worked on this System R project. I decided to stir the pot and really learn not just from research efforts before. I also went and spent a lot of time with product people, and I also dug through a lot of information that had not been documented in any presentations or papers, by in some cases even looking through the code and trying to understand. So it was all this kind of very painful and at times not rewarding in an immediate sense kind of investigations, during the course of which a lot of people wondered within IBM as well as outside, why is Mohan working on something that we all think is a solved problem? It's not the latest buzz topic, it's not the sexiest thing to be working on, it's not like in a sheep mentality way too many people focusing on something and declaring that to be the really important things to work on. So I was doing counter swimming, if you like, because I really felt this brand new project called Starburst, which I decided to, instead of adding functionality to pre-existing systems, design a system from scratch that opened up the possibility for me to, in a clean slate way, address this topic. And even though that wasn't the objective of the project, I decided this is a golden opportunity that doesn't come too often to people, where they get to, from the ground up, build something. And so, but I ought to even convince the people within IBM as well as outside that even though some of them thought this was a solved problem, I had to first convince them that there are problems that had not been solved by others before I even sell my own specific solution. I had to first sell the idea that there is something to be done here, and then argue why the particular approach that I came up with. Of course, there were other people working on it, but I was the primary guy behind this family of protocols.
Inspiring story, I think. Musk said it's more important to find the right problem than solve the problem.
Set of algorithms became so popular, it got into textbooks, which was published in March 1992 in the ACM Transactions on Database Systems.
Okay. So IBM invested huge resources in database field. Also, IBM achieved great success in technology innovation. However, IBM's database business success appears has not matched up with its technical success.
True.
So you experienced all of this history. So from your perspective, why did IBM lose the market? What did IBM do wrong?
Good question, King. So this is the so-called innovators problem, right? That this professor at UC Berkeley wrote a book on, which is when you have something going well, and then you come up with an alternative to that something, then the tendency for the organization that did that first piece of work, which is also now coming up with an alternate way of solving that problem, they begin to wonder, especially if it's a more conservative kind of organization, even if they invent this second approach, which may be more modern, which brings a new perspective on how to solve that first problem in a different way with different characteristics from an ease of use, whatever kind of viewpoint. The worry that the product people have as opposed to research, if they introduce a product based on this newer way of solving that problem, they are worried that the customers who have bought into the first way of solving that problem might get confused, because now there are two alternatives. So in other words, in the database context, IBM already had a pre-relational database product called IMS. It was based on what is called the hierarchical model of data, whereas the relational system like DB2 was based on the relational model of data, which one of my former colleagues invented, this British guy, Ted Cord, in whose name I have an award that I got. He used to be my colleague for 2 years when I joined IBM Research in December '81, and then he retired and he started his own thing and all that. But he is the person who got the Turing Award for the invention of the concept of relational databases. But the other people in my research lab, including my first manager, were the people who created the technology behind realizing that relational concept. We had the legacy in IBM of this hierarchical database system and the related product IMS. So when relational came, the product guys were not eager to commercialize it. Oracle, on the other hand, didn't have any history to deal with. They read the papers written by my predecessors, the System R people. They said, okay, this is a new paradigm for how to manage the data. That is going to be revolutionary compared to the old way of doing it in the hierarchical data model. Because in the hierarchical way of doing things, you as a programmer who accesses the database had to do a lot more things in your application program in order to access the data, especially if you are interested in producing reports and such things, meaning you are trying to analyze the data in a more comprehensive way and create reports and determine trends, what is currently popular as data analytics. You have to write application programs with a lot of imperative logic to do that because there was no high-level query language. Whereas in SQL, but this pre-relational system was very good in short and sweet transactions, like airline reservations, inventory control, manufacturing-related transactions where you look up one piece of information or you enter a piece of information or modify the address of an employee or whatever, inventory control and all these kinds of things they were good at. But when it came to analytics, that system was not good because it didn't have a high-level query language. Whereas SQL had that capability. So the Oracle guys immediately felt, because IBM didn't patent this technology and wrote these papers giving the details of the syntax and semantics of SQL, they quickly built a system and started selling it. And that's when the IBM research guys went and beat up on the IBM product guys and said, what nonsense is this? We invented the technology and this other company is beginning to make money off of it. That was the initial problem. So then quickly the product guys in IBM released the research prototype, the system R, as a product, which was not yet quite ready for commercialization. It had some, prototype-ish kind of way of doing things. But it was a knee-jerk reaction to the fact that Oracle had released it. Now you might ask, why couldn't they after that then, still beat up on Oracle and other companies? Yeah. This is where the initial focus in IBM of only dealing with IBM's own hardware and operating system and all that became a stumbling block. It was a while after the initial release of DB2 before IBM decided that it will port DB2 to run on other companies' hardware products as well as software like the Sun operating system or the HP UX, HP's Unix operating system and so on. And then the following problem came, meaning when you had independent software vendors like Oracle, Sybase, Informix, they didn't have their own hardware or they didn't have their own operating system. Whereas when IBM's DB2 ran on HP UX or Sun OS, the concern that those vendors, hardware people as well as operating system people had in selling the DB2 on those platforms was IBM might use the DB2 product as a foot in the door to get into some customer shop, which otherwise was not an IBM shop, and then they might later on replace their HP or Sun hardware with IBM hardware. So what that meant was the HP and the Sun people would rather have the independent software vendors products like Sybase, Oracle, or Informix than the DB2 product. So it was this kind of compounding effect of IBM being thought of as soup to nuts kind of top to bottom one-stop shopping place that also came in the way of our software running on other people's hardware and operating systems didn't quite succeed as much as people in IBM thought it would when IBM finally decided to make its middleware run on other people's hardware and operating systems. I hope that at least partly explains the difficulties we got into. And by the way, the similar situation came about when IBM invented RISC technology. The mainframe product people were not too eager to commercialize the RISC technology because they said, why rock the boat? Customers are already buying our mainframes and it's a high profit margin business. And we might jeopardize that market if we now confuse the customers by also releasing an alternate way of building hardware, which is the RISC technology. So that happened many years after the disaster with the Relational, where we invented it, others benefited. So in the case of RISC, it was HP and Sun, and even people in Berkeley and Stanford who got more glory outside, in the outside world. Even though the IBM researcher from T.J. Watson Research Center, John Koch, was the first person to get the Turing Award for RISC technology. But from a commercial perspective, we didn't get anywhere as much business because we were late in releasing a product.
Oh, you told us a very wonderful story. Again, prove that technical success is not necessarily means business success.
And I keep telling people also, even as individuals, people cannot think, oh, my job is to sit in one corner, do great technical work, the rest of it will automatically follow. Other people will realize I've done some great stuff and give me rewards and, give me glory and so on. I say that you also have to market your work, even individual technical people, let alone organizations as a whole, also having to say that it's not enough to produce good technical stuff, but you have to also worry about the rest of the story and have a convincing story, use cases and such.
I think it's something that all of the companies should keep in mind.
Exactly.
So, Mohan, you are well-established experts. So could you briefly explain to us why we need a vector database now? And what's the difference between the vector database and the traditional database? And what's the main application scenarios of a vector database?
So this is in the context of this evolution of the types of data that have been produced over a long period of time, from the time of this pre-relational databases to then the initial stages of relational, when we all dealt with what has come to be called the structured data, very well defined record structures with certain number of fields and certain data types for those fields, which all were done in the context of more traditional businesses and such. Then came the revolution, if you like, of big data and so on, and also the usage of IT systems in a much broader context than mainstream businesses resulted in things like social media and such, audio, video, and text and such data having to be managed in the same way in which the structured data was managed, meaning transactionally and in a very efficient way and with a lot of reliability and backup and restore and worrying about disasters and so on. So it's in that context that over the long period of time that database systems have been around, we went from having pre-relational systems to relational systems, and then this whole chaos that came about with NoSQL systems and big data systems. And so it's in that context that some of the vendors or research groups and so on said, oh, the relational systems which are good at managing structured data are not really that good, or they are too expensive. Expense in the sense of dollars and yuan, or expense in the sense of instructions to be executed, performance kind of expense. And so they developed application-specific, very niche kind of systems, these NoSQL systems, which especially had the problem that the APIs were very non-standard and unique across these different systems. The application programming interfaces, there was no standard like SQL, which had been agreed upon across the globe and so on. And then came all this AI, born again kind of AI revolution. By the way, AI has been around since, the phrase itself has been around since 1956. I was 1 year old when that phrase came into existence with a workshop in Dartmouth University in the east coast of the US. But it had been hyped a lot initially, and then it didn't live up to the hype, and then people sort of moved away from AI and didn't spend too much effort. Again, it got born again with the evolution of things like deep learning and such, and more recently with even large language models and such. So along this growth of this whole set of developments, or the emergence of these kinds of new use cases, social media and even IoT kind of devices and streaming of data, vast amounts of data and so on, there was this need for being able to compare images and such, or audio recordings and such, and try to see if you gave one image and you are interested in retrieving other images which are exactly like that or sort of like that. This is where you had to find a way to characterize in a short and sweet way what an image is all about. So this is what's called feature extraction. You can, for instance, think of the color of the image or the structure of the image. You can, characterize this image as it's primarily the image of a cat. This is primarily the image of a dog. But what does that really mean in bits and bytes kind of way of representing it? That's where these vectors come into play. They translate from the image, as one example, to a string of bits that represent certain aspects of this image. Exactly how that's done is somewhat orthogonal. But once you represent this image, characterize the image in a vector, then you can talk about comparing two different images, vectors, and trying to define a way of characterizing what the distance is between these two vectors. The closer they are, that means that the two images are exactly the same or they are very similar. So this is no different from, you can look at a map and say, oh, these two towns are close by, hence various aspects about them will be similar. The language people there speak, or the food that's grown there, or the weather pattern there will be similar. Whereas if you look at two places that are widely apart, then there will be many things that will be different about them. The question was how to represent these vectors in database systems and how to index them so that when a user wants to know, he has watched movies of this kind before. Now we want to recommend other movies which are quote unquote similar to the ones that King has watched. That's all very vague, right? You probably have wondered, right, when you went to Netflix and it says, or you go to Amazon, it says, oh, you purchase these books, you might be interested in these other books. That's all based on this kind of feature extraction, representing it, and recommendation systems all the time are doing this. So what happened was, just like I said about NoSQL database systems and such, where for certain specific data types or use cases, some people chose to come up with a special purpose system instead of using a general purpose system. There are now people who have developed specifically for managing vectors, vector databases. And then there are others who are enhancing existing relational databases with the ability to also do vector data storage and management and retrieval and so on. And so this is like now a debate. In fact, I was at a conference a few months ago this year where they actually had a panel discussion. Is there a need for vector databases, or should we just enhance relational databases with vector functionality? And in fact, in one of these conferences, Oracle guys came and talked about how they've added vectors to Oracle, and also Google guys came and talked about how Google Spanner and Google Alloy DB, they have added vectors.
So from the long perspective, will the relational database with integrated vector libraries become mainstream?
Feeling it's the evolution of relational with vectors that's going to become the more common thing. And this is consistent with what has happened with other kinds of situations where initially, like for instance, object-oriented databases, where a different kind of database system that got created by some startups, and then the relational vendors added so-called object relational features. And the more recent thing along those lines is a whole bunch of graph database systems got created with incompatible interfaces and all that. The more recent trend even there is for the standards community to come out with extensions to SQL to manage graph data, and also come out with so-called native graph manipulation APIs with a standard language. Having too many disparate systems for point functionalities is not conducive to, in the long run, having more interoperability and all these sorts of things, because the application areas tend to evolve. What you might have thought of as a very narrowly defined use case, invariably over time will be forced to deal with other kinds of data than the initial thing that it was supposed to deal with. And so in that sense, trying to have multiple kinds of things in a single system is better than for each thing having its own system.
So besides vector libraries, in which direction the database technology will develop
so for instance,
under the drive of AI?
Yeah, so there is a lot of work that's in progress, and some of it has been announced, which has to do with how to make database systems self-managing, in the sense of, unlike in the good old days where we used to have a lot of system admins and database admins whose job it was to, in greater detail, understand the inner workings of database systems as well as the external APIs and such, and have a much more comprehensive knowledge of the interactions between different aspects of the system. More and more, in the interest of higher productivity and such things, as well as even for the cloud vendors to make the different cloud vendors be, more efficient in supporting their customers. They are all trying to reduce the need for human involvement. So inside of the database systems themselves, decisions like when data should be backed up, when data should be reorganized, and so on, are more and more going to be decisions that are made by self-monitoring and leveraging of AI technologies. Even in the query processing area, in the good old days, we used to have very detailed cost models to evaluate different ways of executing queries in order to pick the optimal way of executing a given query. Those have also had a tough time evolving as new hardware products come about. Things like GPUs and SSDs and byte addressable non-volatile memories, or new communication technologies like RDMA and such. So there are, and even disk drives and such, where their densities change and things like that. So optical drives and such. So in order for these systems to be easier to evolve as the surrounding stuff evolves, memory technologies and various things, communication technologies, it's better if the systems are self-tuning, or they're able to dynamically determine, rather than hardwired into them, the characteristics of the CPU that they are running on and the memory capacity that they have, and over time, as these things change also dynamically, the system can adapt itself to take into account the changed circumstances. So, so there is this concept of AI for databases and database for AI. How to leverage database technologies to make the AI pipeline be done more efficiently, like data cleansing and such things that have been studied in more traditional database contexts to be brought to bear in making the building of AI models and all that be done with less human involvement. And the other way is how to make database systems benefit from machine learning and such ideas for the database system to be less human dependent and more dynamic and more adaptive and things like that.
So let's dive into deeper. Do you think can the rational database architecture way in which one master and several slavers, this kind of architecture can meet the new requirements of large language models for data management?
So I mean, see, even without AI coming into the picture, the emergence of the cloud itself has caused the internal architectures of database systems to evolve. From the on-prem environment to the cloud environment, the pre-existing database systems in the on-prem environment have had to be dramatically changed in terms of their internal architecture to account for the fact that in the cloud environment, we have what's called storage disaggregation. You have a whole bunch of nodes that are managing the persistent data. They are the storage nodes. And then you have dynamically allocated nodes for a particular database that are the so-called compute nodes. These are more or less memory-less servers. So based on a particular query's needs or across different queries that are simultaneously being executed, that is the workload of the moment, more or less of these compute servers will be brought to bear in dealing with that workload. So this is the selling point of the cloud, right? Instead of different organizations having their own data centers and having to pay a lot of money upfront in terms of capital expense, peak capacity a lot of times determining how much you buy, and then at non-peak times these resources are wasted because there isn't enough workload to keep them busy and they are not available for some other organization to make use of. Whereas in the cloud you are consolidating all these resources and you can dynamically change the association between a machine and the particular user that makes use of it versus at another time some other user makes use of that resource. So it's these sorts of changes in the way resources get allocated and deallocated as time goes on that has required significant change to the internal architecture. And one of them is sort of like what you were saying, which is a lot of these cloud database systems today have the restriction that only one of those compute nodes can do both reads and writes. The other compute nodes are able to do only reads. So your update capacity, the amount of updates you can handle at any given time, are bound by the capacity of that one read-write node. And this is something that is not a, forever it has to be that way kind of situation. It's just that people haven't bothered to extend this architecture to allow for multiple read-write nodes. And I actually personally had worked on that sort of topic in the non-cloud environment. And Oracle guys also have done it. I did it in the context of DB2. It's just that the cloud database vendors haven't taken enough trouble to learn from all the various problems relating to multiple read-write nodes that we have solved and adapt them to the cloud environment. So that's one thing. So my point is, relational systems have demonstrated that they are capable of evolving to accommodate changed circumstances. Now you are asking me, can they also evolve to deal with LLMs and such? And the answer is yes, but there will still be some new things that will come up that will require more innovation and so on. It won't be like straightforward. And already LLMs are being leveraged in the context of relational databases, for instance, to support the natural language querying of databases. So the users post queries using natural language, and then the LLM technology is being used to then translate these natural language queries to SQL queries. The problem there is natural language is very ambiguous. So when you do this translation, the system would have to pick one amongst many possible interpretations of this natural language query. Now the issue is, how does the user who posts the natural language query get to tell the system, hey, that's not the interpretation that's behind my query? Because if the user is too naive a user and doesn't know SQL, the translated version of the natural language to SQL query, if it's shown by the DBMS, this person can't figure out what that interpretation is, because they don't know the details of SQL way of specifying the query. And so there's work to be done in that space. If the person is a SQL knowledgeable person, then they can check whether the interpretation is what was in their mind. But then the question is, if they already know SQL, why are they bothering to post the query to begin with in natural language? Is it really a beneficial thing for a SQL knowledgeable person to post natural language query? And some of these sorts of topics have been worked on forever. When I joined IBM Research 43 years ago, Ted Cott, the father of relational databases, had a project in my research lab whose goal was to provide natural language access to System R, believe it or not.
Really? Yeah, looks the history always repeating. So, it's very interesting to compare with the cloud computing era to today's LLM era. So, AWS database suddenly rose up as a new force during the spring up the cloud computing. So do you think there will be a new force of database will emerge under the AI situation?
Good question. Yeah, I mean, that's a good viewpoint to take and ask that question. And it's no different from, there was no Oracle when pre-relational database systems existed. And then when the IBM guys invented Relational and they freely published their work, this new startup Oracle essentially read those papers and came out with the technology. So in that sense, yes, I mean, even risk technology, there were startups that came out that became big deal later on, because they come in without any baggage of pre-existing customer base, pre-existing code and people and such that have a vested interest in prolonging the old way of doing things. So in that sense, yeah, sure, that could happen. I'm not saying it cannot happen. And in some sense, if you look at even vendors like Databricks and Snowflake and such, CockroachDB or OceanBase coming out of Alibaba, or GaussDB coming out of Huawei, they are all players who are younger, much younger than the likes of IBM and Oracle and also Microsoft. For the longest time, Microsoft SQL Server was nothing but a logoed version of Sybase. Microsoft didn't do any work. They just took Sybase and put their name on it and sold it. Of course, with permission from Sybase. But later on, they then got the code base from Sybase after paying a lot of money. And then they did a cut and run modification of Sybase code, and they legitimately then had their own people doing enhancements and such. That's how SQL Server evolved. Even record locking got introduced in parallel by the original Sybase product evolving to have record locking, and the Microsoft guys' code base that they took with page locking from Sybase. they independently implemented record logging, both sets of people using my ARIES technology. So in that sense, yes, it's quite possible that some other vendors could come out of the blue and do something that's more a quote-unquote AI database. But in many ways, even Google, for that matter, which had been in the database business for a long time, but produced middleware that was only used within Google by their own so-called product areas, a captive customer base, if you like. They then, when they established the Google Cloud as an entity for outsiders to make use of Google's resources, compute resources and so on, then they decided to take some of their own middleware and make a subset of them available through the Google Cloud and try to make money. Things like Google Spanner and such. And more recently, they even developed 2 years ago a product called AlloyDB, which in many ways is similar to what you said about AWS, which produced something called Aurora for MySQL and Aurora for PostgreSQL. So AlloyDB is extremely similar to Aurora for PostgreSQL. So it was a new system they built. It was not one of their pre-existing middleware that had been internally used forever, like Spanner. And so Google is relatively new with respect to the rest of the world in the database business. So I can imagine, and by the way, even some of this vector search that we talked about before, Google has leveraged some of the vector technology they had that had been used for internet search, now in the context of AlloyDB and Spanner. So this year there were many presentations in the top database conferences where some of these enhanced versions of the pre-existing systems with vector capabilities got discussed and presented. So Oracle as well as Google, and this NLP support to query databases got presented by Amazon people and Microsoft people in this year's ACM SIGMOD conference.
Okay, people said AWS database changed the pattern of database business because they supplied on the cloud the Aurora, ARIES, DynamoDB, so many different database services.
Redshift is the more recent one, which is the data warehouse. Redshift.
So do you think the new AI database force will change the pattern of database
It could. I mean, but there'll always be these counter arguments to coming up with totally brand new database systems versus evolving what's already there. This has to do with how much of new skilling that you have to acquire in order to make use of anything that has its own APIs and such, which are not compatible with pre-existing ways of doing database management, right? And one of the things that I didn't mention before, which is relevant in this context, is this business of data being moved to computation versus computation moving to data. So one of the recent things that has happened is that, for instance, Google's AlloyDB allows you to make some of the AI algorithms be invocable as part of SQL queries, so that while you are searching through the database, instead of waiting for all the data that needs to be fed into an AI system to be retrieved all the way to the top of the database system, and then separately invoking the AI machine learning models and such, they are now permitting you by allowing you to invoke the so-called vertex AI functions of their way of doing AI as part of SQL queries. Just like for a long time SQL queries have allowed you to invoke user-defined functions and table functions and such. So it's this alternate way in which also some of the disparate functionality is being brought together. there'll be, similar things have happened in the past where people used to have separate text management systems that were distinct from database systems. Then after a while, database systems, relational database systems in particular, started supporting text as a type and allowing for text indexing, similar to document databases like Lotus Notes and MongoDB and such things, which emerged originally as document database systems, and they thought those things had to be done very differently from how relational was managing structured data.
You are the database history yourself. You are the first guy had the industry background I interviewed with, and you really give us different angles and different opinions. Thank you so much, and I hope for your book.
Thank you.
You mentioned the System I.
Right.
I'm fans of System I because I like integrated system.
So you might be actually talking about the System 38 that became I series and AS400. You may be thinking of the System I series.
Yeah.
That's a computer.
Oh, it's totally different.
Totally different.
Okay.
When I say System R, it's for relational. But interestingly enough, in the I series, they did have support for relational databases in the operating system.